Good evening, afternoon, everybody. Welcome to the session Education Tools and Methods. My name is Janne-Markus Rintala. I'm from the ICOS ERIC head office, and I'm chairing this session. The first presentation is given by Martin Steinbacher, and it's about the importance of training for long-term operations of atmospheric greenhouse gas observations. Martin, the floor is yours.
Thank you, Janne, for the short introduction and for giving me the word. Good afternoon, everybody out there. Let's see, here we are. I think I can be short after 2.5 days of very excellent presentations. I can be maybe short with the motivation why we are interested in greenhouse gases, but for sure the atmospheric abundance of greenhouse gases is one of the prime drivers of climate change. The observations need to be of very good quality, high precision and global consistency. And there are networks like ICOS, you're all familiar with that, out there that produce highly compatible data over a large area, but you also know this figure, this is in case of ICOS, this is only the case for Europe and a couple of overseas territories. But it looks different when we look at the global scale, and there are still some areas in the world where high quality data are still sparse, especially in the tropics and the southern hemisphere and in developing countries. This we can also see when we look at the map of the World Data Center for Greenhouse Gases data summary. There we see that this confirms what I said before, that the data coverage is pretty good in Europe and in the US, but in other world regions there are hardly any data. The World Data Center for Greenhouse Gases is the official data repository of the WMO Global Atmosphere Watch Program, and WMO also gathers every other year. Oops, I clicked on the wrong bottom here. Every other year, it gathers greenhouse gas experts in the Greenhouse Gas Measurement Techniques Conference. And the last one was about a year ago, and the report was published this August. And there, the report also states that building expertise in developing countries, including the establishment of high-quality measurement capabilities, remains a critical issue for achieving adequate spatial coverage of the globe in the coming decade. The Global Atmosphere Watch Program has a pretty comprehensive measurement quality framework, with similar to ICOS, but it's a bit more complex because it's not only about greenhouse gases but also aerosols, upper atmosphere ozone, and so forth. But we have central calibration labs, the GAW stations, the stations we see here at the bottom, and then we have also so-called quality assurance science activity centers. There are 5 of them established, and EMPA runs one of these QSACs, and in the GAW implementation plan there's also kind of a task list, and when you look at QA number 6, it says provide training, long-term technical help for station scientists and technicians, or QA3, provide advice and support of local quality assurance systems at individual GAW sites. And now in the following I would like to present some of our experience we made during the last couple of years. But this just repeats again that especially for greenhouse gases, a very comprehensive quality management framework is required, because the compatibility goals, as you can see in this report, is about 0.1 ppm, and you all know that we are at about 400 ppm in the atmosphere. That means it's 0.1 ppm is less than a quarter per mil we want to achieve. And still there are some data like that in the data repository, simply a poorly calibrated instrument reported data. But this is actually an easy case, but there are other data that look pretty good, but if you have a very close look at it, there's maybe still calibration, adequate calibration is still lacking. As I said, we operate the QSAC Switzerland, and we have so-called twinning partnerships with a couple of stations, very close collaboration Here you see some photos of a station in Kenya, Indonesia, Chile, Vietnam, and Kyrgyzstan. And when you start with hardly anything, only basic equipment and the willingness to operate, to generate high quality air quality observations, then QSAC tries to support them with which instrument to use, how to set it up, how to operate it. Once it's up and running, things fail, we try to support when there's some troubleshooting required. Spare parts, you need adequate budget for that, and then once there are data, you need to properly process them. And at a later stage, we also try to do some research, support proposal writing, and to publish the data. And once that is successfully done, we have a fully autonomous monitoring station with high quality data and a good visibility in the Global Atmosphere Watch and the scientific community. And our experience says that this needs at least 10 years or even more. It means just going there, installing equipment, teaching them for a couple of days, and then let them go. This is usually not very, very sustainable. Well, it starts very simple. What do you need? What do the stations need? Usually this is the easy part. Well, you need shelter, you need a mast to install your inlet. You need reliable power. You need air conditioning, especially in the tropics when it can get really hot in the shelter. You need internet access to the station. This is also not given everywhere. Let's think of monsoon, things like that. You need local support. Sometimes it's just to press a button. Usually you should have somebody up close to the station at least 5 days a week, let's say. And it gets, when we look at the second list, still many things are kind of trivial, but if you approach countries that are not experienced with that, they start to struggle, because after we are approached, some institutions say, okay, we found some money to purchase an adequate analyzer, but then they forget that that's not all. You need periphery, you need calibration, you need valves to switch from ambient air to calibration gases, you need the calibration gases, you need the pressure reducers, you need plumbing, you need tubing, well, you need a separate data logger, you need documentation tools, and once everything is up and running, you also need spare parts, consumable, maybe a backup instrument in case something fails. And well, usually there's a graphical, maybe hard to see, but I like to show this one, that you do not only need the blue analyzer here, but if you to get data that can make it to the central database that are highly quality controlled and calibrated, you also need, as I said, all the other things around. Let's see. Okay, where can you get training? Usually we provide training, especially to our twinning stations, but this is only a small number. The most common way to get some training is the GORTEC, the GOR Training Education Center. It's organized by the QSAC Germany, supported by WMO, the German Environment Agency, and Bavaria. It organizes 2 courses per year with changing topics. Sometimes it's greenhouse gases, sometimes it's aerosols, reactive gases, whatsoever. Usually 12 people at the Zugspitze mountain. They have pretty much fun there. And I try to teach there, at least when it's about greenhouse gases. I go there for a day or 2 as an external teacher. And we try to also to open instruments to see how our instruments functioning, how to handle high pressure cylinders and things like that. There are other, maybe less regular opportunities. Here I just highlight 3 of them. That in Indonesia, the Indonesian colleagues from the BMKG, they organize maybe every second year a GOR conference, and last time at least we had an additional day with training. we provided 1-week training course some years back in time in Bolivia for urban air quality monitoring stations. Then there are this School of Atmospheric Measurements in Latin America and the Caribbean. The last time took place in 2018, I think. And there are some others that some other irregular events that are very good resources to get trained. So watch out to find these events. Well, hands-on training operation of the measurements, that's one thing, but the second thing is the data processing. And there, well, for sure, automated procedures are encouraged, but we see that this is often not the case. There are a few tools. For example, Ludwig Ries from the German Environmental Agency, he developed a DAFID data analysis tool. He also teaches that usually at the GORTEC courses. There are others like within the ICOS, at the ICOS Atmospheric Thematic Center, nicely illustration where you can flag data and correct data. Okay, this is maybe hard to see, but this illustrates nicely that you have to split your data into ambient air data, calibration gas data, target gas data. You have to flag the stabilization times in between. And since our partners are often the meteorological services, it is different from simple meteorological observations where you usually expose a temperature sensor and you just let it run without any quality control, let's say for a year, while the greenhouse gas measurements need to be calibrated every couple of days. We also developed some specific tools just to overcome the barriers working with source codes, but for sure, simple, that's an R code, for example, it illustrates that a simple code that also does its job very well. But often we see that the operators have some inhibitions to work with these codes. And well, okay, these tools, they facilitate diagnostic quality control. They can also will also allow for reprocessing once something changes in the calibration hierarchy. That's all the scales. And we see that teaching the data processing side is often more challenging than the hands-on operation, because this is so diverse. It depends on the data logger, on the data format, the calibration strategy, that this needs to be very specific. Okay, well, joint troubleshooting, this is once it's up and running, this is lessons learned during operation. We try to support emails, telephone, whatever, Skype calls. We try to do that. We prepare checklists usually, what to do every week, every month, every 3 months, whatsoever. There's a new measurement guidelines are in preparation, where these hands-on things usually should be described step by step, while the greenhouse gas measurement techniques report more gives the overall setting. And we plan video tutorials and recordings of online seminars. This is one of the positive things of the pandemic, that now people are really getting used to these online tools. Obstacles, very short. Arlene Andrews already identified similar things on Tuesday morning. She also said the lack of resources and logistic challenges are key. This is what we also feel. Then there's also some hierarchy issues. Who's responsible for what, and unclear responsibilities within an institution and among the partners. Sometimes they rely on us. We try to teach them that they do the quality control and things like that. Language barriers for sure. Okay, and I think brings me to my conclusions. I just want to show that the capacity building is a very lengthy process. Please be patient. 10 years, I think we need to commit ourselves at least for 10 years, we would say. Coordinated efforts would be helpful to coordinate training, to promote training, to broadcast that their training activities, to open them for others. Exact exchange of lesson learned. I'm also looking forward to the following talks in this session about capacity building and tick lists. I think it needs to be more. We need more blunt tick lists. What you need that when our partners start from scratch, that they really think of the most, at least of the most important things. And I would like to thank Media Swiss for funding of the Quality Assurance Science Activity Center Switzerland for many years, and I would like to thank you for your attention. Thank you.
Thank you, Martin, for a very inspiring talk. I especially like that you made a long list of requirements, not only the instrument, that being very comprehensive in it. Do you have an estimate of cost, how much it does take to build one? If somebody now gets so inspired that they want to apply funding now to put up a station somewhere.
How much it costs to build a station? Well, it depends on the measurement program, but greenhouse gases, I think our best guess is 300 to 400,000 US dollar. Well, the biggest part is the analyzer, but then you need, on top of that, you need at least the same amount of money maybe for the periphery.
And I'm also interested in it that you say that the funding or the training, we need to dedicate ourselves for our students, at least minimum of 10 years. And that requires loyalty from the funding sources as well. And there is also a question from the chat that do the partner institute staff stay for 10 years? That's also a problem with your PhD students or postdocs whom are maintaining. So can you very rapidly answer that?
Well, the situation is, I think, even worse in some of the countries we collaborate with, that they are moved away to another station that is not doing air quality measurements anymore, and changes in staff. This is a real issue. If we could visit a station every second year, let's say, half of the staff is usually gone.
Yeah. All right. In 2 seconds, can you reply, do you miss your students abroad now when it's COVID and we're not allowed to travel?
Yes. The short one is yes.
Thank you, Martin. Now we need to move on to our next speaker, which will be then Laura Riuttanen, and she's from the University of Helsinki, and she will be talking about learning multidisciplinary climate change competencies. Go ahead, Laura, the floor is yours.
Thank you. Let's see how this works. So I am Laura Riuttanen from the University of Helsinki, Institute of Atmospheric and Earth System Research. And this is the outline of my presentation. So I will first introduce you our inner edu team, and then discuss what are climate change competencies and tell some highlights of our very recent study. Then I will introduce you Climate University, the project that I'm leading, and some of our inner intensive courses with references. So in the Institute of Atmospheric and Earth System Research, University of Helsinki, we have a rather new and active research group that is concentrating on education, research and development. And we are atmospheric scientists by background, but now very interested in and concentrating at learning of atmospheric sciences. So here is the link to our webpage. You're welcome to visit and contact us if you're also interested in studying the learning and teaching of atmospheric and earth system sciences. In this presentation here, I have some highlights of my very recent study that is now under review in Tellus B, the Euroflux special issue, where we ask, do the competencies taught in atmospheric and earth system sciences respond to the societal need for climate action? So we have studied atmospheric and earth system science study programs and teachers, and ask them what kind of competencies do they teach in their teaching and in their study programs, and then we discuss how this relates to the current societal need for climate change actions. So what is a competency or competencies? Competencies are knowledge in addition to skills or abilities, as well as attitudes in a certain context with a certain purpose. And in this study, we studied the general academic competencies that might be familiar and teach for long. Those are, for example, applying knowledge, collaboration and communication skills, analyzing and structuring information, seeing different perspectives, critical thinking, making arguments and looking for solutions, as well as developing new ideas. And in addition to those, we also studied competencies of sustainability that have been defined by Wieck et al. And applied in the field of sustainability sciences. And those are systems thinking competencies, anticipatory competencies, normative competencies, strategic competencies, and interpersonal competencies. And we sent a survey out to teachers of atmospheric and earth system sciences and program representatives of 17 educational programs in the field of atmospheric and earth system sciences in Europe. And we selected the programs by those who are included in our ABS teacher network, with its atmospheric and biosphere studies teacher network, a quite active Nordic Baltic network of teachers in the field, as well as the Euroflux network, more specifically those who attended the Euroflux workshop in Finland in December 2018. And in total, we had 17 educational programs in those networks. We got 9 + 6 answers, so the number is not so large. So these are mainly indicative results, not quantitative, but in general we think that this represents the field of teaching of atmospheric and earth system sciences. So we asked them about how much they teach these different competencies, but also how familiar those competencies are to them and how important they consider these different competencies. And we figured a teaching gap, so that if they see a certain competence very important, but it's not so much in their teaching, we saw that there is a teaching gap. And for example, we see a teaching gap in collaboration and communication skills, as well as interpersonal competencies. So those are seen as very important competencies for the students to learn, but they are not so much present in the current teaching. As well as making arguments and looking for new solutions, or competencies of developing new ideas. In those, we also saw a teaching gap. Then we asked the teachers and study programs about teaching collaboration, and all of the study programs had already teaching collaboration, and most wished collaborators were scientists from their own field of science or other natural scientists. The collaborators that were not wished much were artists or activists or non-governmental organizations or life scientists. So to conclude our study, we saw that these general academic competencies were much more familiar to our study group than the sustainability competencies, but this might be natural because these general academic competencies have been taught for decades. And also the sustainability competencies are framed to the framework of sustainability sciences. But we saw here an important need to define what are the competencies we teach in climate sciences and atmospheric and earth system sciences. So we see there is a work to be done. And also we asked about how do the teachers identify themselves as atmospheric scientists or earth system scientists or climate scientists or climate change scientists, and how do they see the expertise they teach to the students. And we found it a bit surprising that those teachers did not identify themselves as climate change experts and didn't find out that they teach expertise in climate change to the students. And here we ask a question that who is then a climate change expert if not the atmospheric and earth system scientists? And might this be a reason why the atmospheric and earth system scientists sometimes hesitate in taking part in societal discussions about climate change? So in total, we aim at raising discussion on these topics, and there might be more open questions than overarching results from our study, but we find this as an important topic to study further. So what are these competencies we want to teach in atmospheric and earth system sciences, and how this relates to the societal needs of climate action at the moment? And I think that one of those competencies we need are the competencies of collaboration, because climate change is such a huge topic that no one can alone handle it. So what kind of collaboration do we as an atmospheric and earth system scientists need to make effective climate action? How to find those collaborations and maintain them? In the end, I would like to advertise Climate University, the project that I am leading. So in Climate University, we are 11 universities from Finland developing climate and sustainability teaching in universities in Finland. And we have produced new online courses open for all on these topics, as well as workshops for university teachers where we workshop teaching of climate and sustainability topics in universities in Finland, and we do collaboration with schools and the working life. And so far we have produced 9 open online courses that are located at the digicampus.fi platform, openly for all. And these courses are 2 to 5 credits each, and a minor of 35 credits can be completed. Out of these, the courses handle basics of sustainability, basics of climate change, systemic thinking in sustainability challenges, statistical tools for climate and atmospheric science, a course about climate communications, circular economy, leadership, as well as a project course where we collect concrete climate and sustainability challenges from the working life, and the students in multidisciplinary groups brainstorm new climate solutions. And all of these materials are online. And our next workshop will be in the beginning of October. It will be online, about partnering science and law for effective climate action. So in collaboration with climate scientists and law people, you are very welcome to join our workshop. And all these details you find from climateuniversity.fi. Then I mentioned also the intensive courses we are running at the Institute of Atmospheric and Earth System Sciences. Some of you might be familiar with the Hyutiellä courses, so intensive data analysis courses we run at the University of Helsinki Hyutiellä measurement station and have had those since 1996. And in a recent paper by Lauri et al., we present the pedagogical approach of those courses, the pedagogy of horizontal learning, where scientists at the different stages of their career study together real research questions and data, and new science has been made at these courses, and they have been found very fruitful to young scientists and more experienced scientists too. And we have also found out that the students at these courses, they learn many transferable skills that are very useful for their working life. And here are the references mentioned. Thank you.
Thank you, Laura, for a very comprehensive presentation. There's already questions coming from the chat, and one thing is that a very critical question nowadays. Do you think that there are any specific competencies needed for climate scientists that you would include, or for instance, responding to climate deniers?
Yeah, that's a very good question. So what is the competency of climate scientists to respond to climate deniers? Maybe argumentation or communication skills might be essential here. But definitely it's not enough that you have the knowledge. You also need to have the abilities and other skills.
And are all of these classes that are open for all, what language are they at?
Yeah, good question. So most of these courses will be in English. Some of them are also in Finnish.
And do you think that they are also suitable for students from, for instance, from Mediterranean or even from tropical?
Yes, they are. You're very welcome to take a look and glance through the materials. So we have tried to keep this global perspective in mind. But I have to say that the Climate Now course, where we started this project, that it was done some years ago to Finnish context, and it is now in use in 9 universities in Finland to teach the basics of climate change. But it has been a bit Finnish perspective in topics, but we are working on, in collaboration with the Nordic-Baltic ABS teacher network, to make Nordic extensions to the Climate Now material, and we would be very happy to collaborate with you others too if we could have some Mediterranean additions, for example, to the Climate Now material to make it more global.
Okay, let's hope that that was heard loud and clear so that you will get an overflow of partners coming from elsewhere. I have a question that, do you include our Jupyter notebook and ICOS data that is free that in your teaching or in these courses?
Yes, in the statistical tools for climate and atmospheric sciences course, we examine open atmospheric data that is available, and the students can choose which data they want to work on during the course and use it in their course during the studies.
Is this the first time you are keeping this course about partnering science and law? Because I'm just wondering that these law students, what are their capabilities to use in statistics overall?
So the workshop in October will be open for anyone. It's not actually a course, but a workshop where anyone is welcome to join and discuss. And we are trying to find connections and how can we join forces with law students and researchers and lawmakers and then climate and atmospheric scientists. So it's kind of new opening not really a cause.
Okay, I look forward to it already, and I think that I will join there. Then I also have a thing that there's lots of climate anxiety, especially in the youth. What's your recommendation? How can we help that? I mean, teach these facts, but still not to cause too much anxiety or fear.
Yes, I think the competencies are very essential here. So it's not enough that we teach the knowledge about climate change, but we have to think what are the competencies that the youth need in living in this kind of changing world with all of these challenges, and how can we teach them also action competencies, so competencies that empower them to take the actions in building a sustainable future.
Thank you, Laura, very much. I think I hope there will be lots more questions in the chat. Please go and answer them. Now, our next talker, Ida Storm, Department of Physical Geography and Ecosystem Science from University of Lund. And please, Ida, the floor is yours. Go ahead.
All right, thank you very much. So the talk today I'm gonna have is characterization of atmospheric stations using footprint analysis. And this is work that I've been doing at the Carbon Portal together with the ICOS Carbon Portal team. And the overview of my presentation today will start by me giving an overview of the characterization variables that I'll be using and showing in visualizations today. Next, I will go over stilt footprints just briefly, because the footprints are the foundation for the characterization. I will then give a short overview of methods, and the bulk of the presentation will be showing visualizations for the ICOS station Traino in France. And already now you should know that these same visualizations that I'm showing or will be showing will be available in PDFs on the station landing pages. So that's in progress and soon, but Traino for now as an example. Another point to make is that there is going to be a Jupyter notebook, and there will be a characterization tool that will be available as a service for users, similar to those you saw Carolina showing this morning. So in the same place, you can find this tool where you can produce the same type of visualization that I will be showing, but with additional parameters that you can specify. And you can also do this characterization for a hypothetical station, since the only thing you need is footprints, and you can generate those. So the station characterization variables that I will be showing or looking at for Traino is where is the influence region of a specific atmosphere station, where we use the average footprint, and it's quantified in maybe a way you haven't seen before. And the next part is what is in the influence region, as well as where I have prepared auxiliary data layers that have been coupled with the footprints, including land cover, population, and point source emitters. And in gray, you see radiocarbon emitters. Radiocarbon emitters within the footprints, that's something that I'm working on currently in collaboration with colleagues in Heidelberg. And a notebook for that will also shortly be available. So first, the where. I've already mentioned that it's the stilt footprints that I've been using. And the stilt is a Lagrangian atmospheric transport model. I won't say too much here, but the resulting footprints for a station are grids with estimated influence of potential surface fluxes within each cell. And throughout the presentation, I refer to this as sensitivity to each cell. And you see here to the left a footprint representing a specific time point in time. And to the right, you see an aggregated footprint for Traino for 2018. And this is the foundation, then the average footprint for 2018 for the characterization. And as a note, you see the type of footprint we see. You can find at the ICOS Carbon Portal webpage in the stilt result viewer. So just follow the link in the slide and you can look at them. modeled carbon dioxide concentration based on stilt footprints coupled with anthropogenic emission data from EDGAR and the biogenic contribution from BPRM can give us an idea of what makes up the concentration at the station. And I'm mentioning this here because 2018 averages are used as characterization variables in some of the visualizations I'll be showing you. And that includes respiration, GEE, which stands for gross ecosystem exchange, and anthropogenic emissions. So again, you see the same footprint as on the last slide. And to the right, you see also what you would see if you went on the stilt result viewer web page. You can, for the specific point in time, in this case in July 1st at 9 o'clock at night, you have the GE component and the respiration and the anthropogenic contribution. Here is the fuel, but you could also get it broken down into fuel types or source categories, but yeah, leaving it as that. And my overview of methods include that the auxiliary data layers I mentioned, for instance, land cover, was aggregated into the stilt model grid. And the stilt model grid is 1/12 of a cell, 1/12 times 1/8 of a degree cells. And over the whole stilt model grid area, that results in 192,000 cells. And for each of these cells, we have an area of, for instance, cropland, which can be, of course, 0 if there's no cropland or any other number. And in terms of the auxiliary data layer population, it's the number of people living within each cell. But the rest of the work for me has taken place in Jupyter Notebook, where I've been programming in Python. And there I took these prepared auxiliary data layers and combined them with stilt footprints. And I can also mention that model concentration values, GE, respiration, and anthropogenic contribution, I accessed directly from the ICOS Carbon Portal server into the notebook. So now we get to some results. Like I said, I'm using Aino as an example. And what you see now is what I call the sensitivity area map, which is the aggregated or average footprint for 2018, but it's binned so that all the cells that are within the same 15 degrees at the same interval, I have 100-kilometer intervals, are summarized. And the percent sensitivity to each of these bins is then the color in the map. And these 15-degree bins, 100-kilometer intervals, it's just something that I've chosen. If you use the online tool, you'll be able to specify this yourself, what you think is appropriate for best visualization. And I also want to say something Aino specific. 30% of the sensitivity is within 200 kilometers, 47% within 400 kilometers. And in terms of direction, 22% of the sensitivity is between 30 and 90 degrees, if you, with then north being 0. I can't show on the map, so you have to visualize it yourself. Next, we see the same type of map with 15-degree bins at 100-kilometer intervals, but instead it's the population that is showing. And I also want to say something kind of specific here. There is high population sensitivity to the area that includes Paris and the neighboring bins, which is no surprise, of course. Also, you can say that 45% of the sensitivity to population is between 330 and 30 degrees of the station. Again, you'll have to visualize that yourself. And the last type of this map that I'll show you, the same binning again, is for point source contribution, where you then see the average contribution of the emissions in the carbon dioxide concentration at the station. So you get a percent from each of these bins. And for Aino, highest contribution comes from 30 to 90 degrees, corresponding to 50% of the contribution. And you could do these type of maps for GE, respiration, and anthropogenic contribution, just to get your wheels turning, because we can always develop more of these type of products. Next, I show you a land cover bar graph. We see the land cover distribution within the average footprint, and the binning here is a little bit different, 45-degree bins, where you can see the breakdown of the different land cover classes. And I have defined northeast here as 22.5 to 67.5 degrees, and then you can do your own calculations for the other directions. And the difference in column height corresponds to that it's simply more sensitivity to the area northeast of Aino station. That's why that's higher. And the Aino specific, the highest sensitivity is to cropland, followed by oceans and forests. So I want to move on, because here is a different way of showing the land cover distribution within the average footprint in a land cover polar graph. And it's again 15-degree bins rather than 45. And the land cover type that is showing closest to the center here is cropland, since that's Aino's highest within the average footprint. But it should be noted that cropland not necessarily is closest to the station. So just want to make that point. And really take a moment and try to understand this graph before you try to make interpretations. We have labeled this one as an advanced figure and should proceed with caution. I also want to say about it that the area of land cover in the graph corresponds to the proportion within the average footprint. And Aino specific again, cropland, you can see is found in all directions of the stations, but more in the northeast and southwest of the station. And here is another one of the figures labeled advanced. It's the multiple variable graph, where the 2018 variable average of the selected station here at Aino is compared to some reference stations. And we have a y-axis ranging between 0 and 100%, where 0 is the station with the lowest variable value, and 100% is the station with the highest variable value. So if we take a moment and look at sensitivity, you can trace that the lowest point there is to Jungfraujoch, whereas the highest point is to ISPRA, IPR 100, yes. And then the rest you can think of yourself here. And for Aino, it's fairly low values compared to the reference stations. That's all I have to say. Also a note here, inclusion of additional stations will of course potentially change the range of the graph if it's a maximum or minimum value. So that's another thing to keep in mind. And here is the final figure I will show you guys today. It's 2018 averages compared to averages for the different seasons. January through March, April through June, July through September, August, October through December. And it's a little bit tricky, maybe. You have the unit farthest to the right, corresponding to the 2018 column. And all the other values are percent difference from that average value. And the average values for sensitivity, population, and point source is just summarizing cell values of all the cells in the graph. And I don't know if I have time to say something Aino specific, so I'm going to skip and go to the next slide, where I'm going to mention that, like I said, the output, there is an output PDF for Aino, which will end up on the station landing page, where you can see all these visualizations, but also information about the station and information on how variables compare to all other ICOS atmospheric stations. And there's also specifications at the end of each PDF, where you have more in-depth descriptions of the different visualizations. You'll have links to the different auxiliary data layer sources and links to additional resources. And I mentioned a tool option that you can go in as a user and explore data, the same links that Carolina showed you this morning. Where you can specify your own parameters, the binning, the intervals and stuff. I have all the parameters listed there. Also the units for the maps, should it be in absolute sensitivity or percent? Do you want to include titles? Maybe if you want to use just a single one of the figures. So yeah, but I'm running out of time, so I'm going to go to my next slide where you just see an example of the tool. You don't see the whole window, but you get the idea. You specify parameters, you get the output, very exciting. You see the progress bar ticking up till it's done. And just a final quick outlook. Just give us feedback. What do you want? Try it out, and also stay tuned for the radiocarbon notebook, which I don't have time to say anything more about. So I'm just gonna say thanks. 7 seconds to go. A little sweaty there.
Thank you, Ida. That was an excellent presentation of very complicated issues. And I must congratulate you. And there's also congratulations in the chat. Claudio Rosendahl has said that very nice graphs and thank you for a nice presentation. It was indeed very complicated issues and matters shown, and your graphs are really visualizing them very nicely. I especially like the ground, the topography stuff that looked a little bit similar as a wind rosette. But yeah, it takes a while before you can understand it. I can clearly see it. How are you going to improve this in the future? What's your next topic? I thought that now this is within 2018 data. Are you now putting other years or what?
Yes, so different years, different data, different relevance. I think maybe the population data doesn't need to be updated as much, but for sure we've thought about making it an annual product where we could maybe update to the latest land cover data, and maybe different land cover data too. We've used the Corinne now and open for suggestion from whatever you guys need and stuff. And also how you aggregate the different land cover classes. Now you only have a few aggregated classes. So yeah, just you guys will guide where we go from here, I think.
Well, I have this personal interest because last winter nearby our farm, all of the fields, they were just flooded. And in the Scandinavia, we normally have ice and then snow on top of that. But now it was so mild, we are calling it a hot winter, that there's lots of riverine flood off and stuff like that. And I noticed that you had mentioned January, March and October, December. And now it would be interesting to see if you could compare the last results from last year with those 218, how this season differs. So it's not only the summers that have become hotter, but it might be also that we need to look at the winter. And therefore, there's also this hot winter initiative now going on, and maybe you would like to participate in that.
Absolutely, that sounds good. And I just want to mention, since you bring up that table, now we're using meteorological seasons, so December, January, February instead of January through March. But just a short note there. Lots have happened in the last couple of weeks since these slides were updated.
Yeah, I can imagine. I think that everybody has been in a rush putting up their presentation. But yeah, I think that it went really remarkably well done, and look forward to hearing more about it in the nearest future. But I think that now we are running out of time. I think there might be more questions coming into the chat because they are coming at a little bit delay. So please go over there and answer and put anything if you want to share like a reference somewhere. So please share that.
Thank you.
Thanks a lot, Ida. And now we are moving on to our next speaker, Claudio Donofrio from the Carbon Portal. And Claudio has a really nice topic called ICOS data at your fingertips. So Claudio, the floor is yours. Go ahead.
Good afternoon. Thank you for having me here. Yes, as you probably have guessed, I am working at the Carbon Portal within the ICOS community. And hence, I would like to go away from the advanced and complicated figures you have just seen from Ida. My talk is more about tools and methods and make it as easy as possible for the users to access the ICOS data. I think it is honoring the work of all the member states and the PIs and all that hard work which is going into measuring and observing and collecting greenhouse gases, going through all the procedures and methods, and then we end up with very nice high quality data sets. And we are at the Carbon Portal have the task to provide you a interface to access this data and then use this work. So my motivation for this one was how can we really make it easy for everybody to access the ICOS data? And for me, easy is as I don't want to be a rocket science. I have a computer science background. I can do a lot of programming, but I don't want to do that. I want just to use the data to concentrate on the science rather than writing scripts as in how to load downloaded data back into my programming environment again. So we dive straight into it. It is a Python library, which I have developed. And while I say I have created and developed, it is the tip of the iceberg. I would like to give credit to the Carbon Portal team. They are not named here, but there is a lot going on in the background from the development team. They have done a fantastic job to have a sound and solid base where then I can come and put something on top of it. So if you know programming a little bit with Python, I am sure you have seen the pypy.org open repository for many libraries available out in the world. It is very easy to install. There are all the links available to the source code, to documentation, to examples. And I have seen in the chat box, there is, I put the links up there as well. We have a public available Jupyter Hub, like a Python interface in your web browser where you can play around and just do whatever you like. You cannot break anything, so be not afraid of just go and play. Installing this library, is as easy as this. It is pip install the ICOS Carbon Portal library, and you're done. There is no more to tell. Sorry. So if you want to access data, there is one thing you need to know. Every data set that the ICOS Carbon Portal has a PID, persistent identification. And you can think of as a DOI for scientific paper, but this is like an identifier for data sets. So this is the one thing you need to know. And the easiest way is you go to the data portal, you browse around. It is a very powerful, nice and search interface. And once you have a data set you would like to work with, you take it either to your Python environment, or you can go, as I mentioned, to this public open available Jupyter Hub where you can play around on our server with the ICOS data. And I think best is to have an example or two. This is the 5 lines I have been talking about in the beginning. So I hope you can see this. There is one line, you load the library, and then there is this a little bit cryptic persistent identification. I come back later to that, how to retrieve it. But at the moment you would go to the data portal, you will find this and you can create a representation in Python for this data set. When you have done this, you can already ask information about this data set, like what kind of columns are available. For this specific example now, we can see there are columns, a flag, quality flag, a number of points, standard deviation, timestamp, and the tracer gas of methane, which has been measured. You might ask, well, how can I cite this data set? Because you have now written a publication and would like to cite this. So it is as easy as putting in citation and you will get back the right answer. Obviously, the next point is how do you get to the data? And it is basically give me the data. There is all what it is. You will get back a table where you see now the content, the real values, the measured values. In this case, it is a level 2 data set. So it is quality controlled, quality assured, ICOS data product for methane. And last but not least, often you would like to see how the data looks like. It is one line, you say data plot, and like a time series, timestamp, the methane over time. And those are the 5 lines, and you have a reproducible, high quality graph, which you haven't downloaded any data or anything, you just used the data. And this was my motivation for this. As I said, you need to go to the data portal and find this PID. The first question I always get, well, but how can I have this in Python? How can I retrieve persistent identification IDs for data sets, and where are they coming from? So at the moment, there is one additional part of this library where you can explore the ICOS stations. And again, it is one line to load the module. And then there is a function called get me the ID list. What you will get is a complete list of all stations from ICOS. And I'm sure you know we have ocean, atmosphere, and ecosystems stations. So you will get back a list with the link to them, the identification, the name, where are they, which country they belong to, what theme they are belonging to, and so on. And because you're now in Python, you can easily make a filter for country or for a spatial selection or for theme or something like this. You can do a representation of one station where you get lots of information, as in contact, where it is, and so on, in a text format, in HTML format, and so on. What you can have as well is a list of what this station has produced, what kind of data. Here in this Zeppelin atmospheric station, you can see, for example, they have provided a data set for the Drought 2018 project you have heard about in the last couple of days as well. And probably the most important bit is now that you can say, well, give me all the persistent identification for all data sets for this station. So this now links back to the first example. You can take this ID and load the data with one more line. Now, what if ICOS is not the only one which has such a library? And I'm talking a little bit now about hopefully the future where loads of data centers with all the data sets have similar approaches. And so what if there is another data portal which does something similar and has very similar data sets and collections? And as an example, maybe a proof of concept, you can call it. There is a very nice data portal, Pangea, in Germany, and they have many, many data sets available. And they have an extremely similar Python library. And as you can see here, the 3 lines we had for ICOS, well, they are duplicated now because we need to load data from another data center as well. So you need to load 2 libraries and 2 data sets. And a couple of more lines and you have a graph, which shows now a boat which was traveling from Europe to South America. One is a ICOS station from the Ocean Thematic Center, from France to Brazil. And this is a plot of water temperature, which is depicted in the different colors. The other one is a data set from Pangea, and there was another ship collecting water temperature and more variables, but this is just for visualization purposes, obviously, which was going down to the very southern tip of South America. And you can see it is very, very similar, the data they have collected. This is just another representation on time, where you can see the boat from Pangea on the left side was traveling a couple of weeks earlier than the ICOS boat, and the temperature rises while crossing the equator, so the water temperature is more. The same goes for citing those data sets. It is as easy as 1 line and you get the proper citation which you can use. We are almost done. Conclusions and outlooks. Well, I think it is a paradigm shift, the thinking of not downloading data, because this is the conventional day. You go, you find data, you download it. You need to make sure that you have the correct version. You need to reorganize it and reload it. And this is all too much hassle. You shouldn't need to think about this. You should be able to just use it. So good to know very quickly, at the moment at least, the search for data and the data sets, it is more powerful online. We have a very nice faceted search interface. I do hope that we can increase the possibilities in the Python library, but if not, then go to the online data portal, that's fine. There is one more point. At the moment, we are only 99% guaranteeing the correctness of the data, because we make a snapshot of the actual data file we have available for you. And everything is open source and available through GitHub, through the PyPy.org website. It is still considered as a beta version, a very stable one. It should work, but please give us feedback. We are here to make this tool for you. It is a little puzzle piece in the whole process, which should make your life easier to make educational notebooks like Ida's and Carolina's presentation have shown today. So we are here to work for you and not the other way around. So I have a few ideas, obviously, to add to the library to make things better and even easier. If you have ideas, please get in contact, let us know. And as an outlook, hopefully we will have a possibility to make your Jupyter notebooks so like you can freeze it and put the DOI on your work as well. And then you don't even need to think about your programming environment again. So this is the message to take home. just go to the Explore Data website. You cannot break anything, just play around, have fun. It is really easy. It is transparent and reproducible. And what we have as well, a collaboration platform. So if you want to use this library on our server with other colleagues for a scientific project, please get in contact. We can arrange that, hopefully. So thank you very much, and it was a pleasure to be here.
Thank you, Claudio, for a very nice talk. And it's really a pleasure you say that I don't have to be a rocket scientist. I'm just a plankton taxonomist. And even I was inspired by this talk. So I promised you that I will go there and I will try to use them as well. I especially like that you also have this comparison to other data portals like the Pangea. So it was really nice. Then there's questions already in the chat. Somebody's asking that will the slides be publicly available after the conference? And so
absolutely.
Yeah, I can also post that into our chat that we will try to make them, but first we will have to get approval from all of the authors, and it will be in SlideShare. Yeah, then there was something. They wonder if you could combine Copernicus and ICOS data. Have you tried that?
No, I have not tried. I have been working very hard to get this library to the current state, but I am very excited to extend it to other data centers like the Pangea one I showed. So hopefully we can have Henry Fair as well, taking this up a little bit so that the whole environmental community can pull together so that we have access to all data sets in a similar fashion.
Great. And then Corinna Rebman is also complimenting you and asking, are these tools applicable for near real-time data or only for the release data?
No, it is level 1 and level 2 data. So be careful. The level 1 data is not the final data product, but yes, you can access near real-time data as well.
Okay, yeah. Then there's more coming on into the chat, I hope, and I encourage everyone to write more questions into the chat, and look forward that you will then continue over there. Any other ideas that you want to share here? What would be the next step, next level in your desire to sort of advance this?
Well, maybe I have to mention that we chose now Python as a kind of proof of concept or showcase because we have this public Jupyter Hub interface as well with Python. But if the demand is there, as we mentioned this morning as well, we can think of doing a C library or R interface if people really need that.
Okay, thank you very much, Claudio. And now it's time to let's play the climate adaptation game. There is a little change in this presentation because, as you know, behind every successful man, there is even more exceptionally talented woman. And now we have a change in a presenter. It's not Pontus Wallin, it's Aino Runegård. Go ahead, Aino.
Oh, thank you for that. I hope I can live up to that. Well, my name is Aino Runegård and I work at SMHI, and I will do this a bit differently perhaps because I don't have a presentation. I will show you this game through my my website. So I hope you all can see it. So this is a communication tool and a game that we at SMHI, the Swedish Meteorological and Hydrological Institute, have done. So you can find it here at our webpage under climate, and then click yourself into the climate game. And I will show this very briefly, but you'll get an idea of how it works. And if you want to, of course, you can play by yourself later on and try it. So let me just take it into the full screen. So what is this? Yeah, it's a computer game, but it's a serious one. So you're responsible for adapting this fictional town of Riuttanen. You have a limited budget, or in this case we have, or I have, of 12,000. You see the wallet up here to the right. You also have to take care of the citizens, as presented here, because lives are at risk, and you can save them by doing good climate adaptation. And then you also have 5 sustainability development goals to reach. And to reach them, you need to have a darker green and a double arrow pointing upwards on all 5 of them. Then you have been successful on that one. So we start in 2020 in this town. And in this town of Riuttanen, we have 3 types of extreme weather. We have 10-year rain. We have 100-year rain. We have a 3-day heat wave, 7-day heat wave, 10-year drought, and 100-year drought. And in the beginning of the game, which I didn't show you, you can choose which RCP to play. I've chosen the middle way. It's RCP 4.5. You can choose 2.6 or 8.5 also. And later on, you will see that we'll make a time jump. And during that time jump, the weather will be randomized within these, probably within these statistics shown here in the bar chart. And as you can see, the chance of getting hit by, for example, a 3-day heat wave is much larger in the end of the century. So we have 7 missions in this game, and I won't be able to show you all missions, because if we do a workshop, normally it takes 1.5 hours to 2 hours. And we divide people into groups and have group discussions and such. But you'll get a sneak peek. This is adapting agriculture to drought. And in all missions, we have 4 different alternatives. And we also have explanation why to do this. So it says that for the past few years, we have seen longer periods of drought causing big losses in harvest. And the question is if we want to implement any of the following measures. And if we click into these, you can see what it means. By choosing A, it costs us 500 coins or money to construct, and 250 to maintain in maintenance costs. And in A, we replace the crops with more drought-resisting crops on half the fields. And here, down here, we can also see how it will affect the SDGs, or 4 of them is affected, and what will happen if we get hit by a drought. So we can see what economical effect that would have on our town. And this you can see then for all of them. Here we have B. It's a bit more expensive in construction cost and in maintenance cost, but we also have an irrigation system and a pond to collect rainwater. And then we see that 2 of the SDGs are negatively affected by this, but we are better adapted for drought. And then we have option C, which is the same as A and B, but we also have a dissemination plant, which also takes a lot of energy. So it, it affects this goal negatively. And we always can choose X, which is to do nothing. If we want to put our money elsewhere, or we don't have enough money, because that's a reality too. So for this, I'll choose A. Then we have densify the city as the next mission. And as we can see here, option C is no longer available for us because it's too costly. But we have a need of new housing in the city to have an increased population. And if we look at A here, we have for 8,000, we built more houses with individual parking lots for all apartments. And every apartment has at least one car or place for that. And it's dark facades and hard surfaces. So this is not quite climate adapted. And as you can see, it affects most of the SDGs negatively. And here we can also see that a heat wave would cost us a lot of money and a heavy rain also. For B, we have a greener city, and we also have, on A2, we have a tax income if we get more people into the city. And here we affect all the SDGs positively because we have more green areas and we have carpool parking. And here you can see how it will affect us if we get heat waves or hit by heavy rain. So I won't even show you C. I'll just choose B so we can do the time jump. And you'll see what I meant by that the weather is randomized because we have no idea what weather will hit us. So we had a bit of bad luck. We had 100-year rain. This could happen. You never know what happens. And we also had 3 10-year rains and 2 3-day heat waves. Unfortunately, we didn't save all the lives that were in danger, but we affected the global goals positively. And we have some money left in our wallet for the next time jump. Here I will also tell you who we had in mind when we developed this. It was students in the age group of 15 to 20 years, perhaps. But however, we also have played with politicians, meteorologists, municipalities, and many more. So it's a fun way to introduce climate adaptation and the difficulties with it. So it could be used as an icebreaker. I'll show you here that we have a mission called Save the Hospital from Flooding, because here in Riuttanen, the hospital is placed quite badly. It's if we get hit by a heavy rain, it could be flooded, which of course could cost lives. So here we can see that we have an option to invest in mobile flood barriers, which is sandbags for 1,000 in construction or cost and an additional 500 in maintenance cost. But we can see that compared to X, by doing nothing, this is still, it's a good alternative. And in B, we have a ditch and a rainwater pond and still the sandbags, but it's more expensive. And we can see that the rains won't cost us as much. And for C, we have a permanent barrier, and we also have a new highway exit. That means that the ambulance could travel to and from the hospital at all times, which of course is very good. And we also see that we don't get economically hit that hard by a heavy rain. And then we have the X, that is doing nothing. The two fellows here are if you want help for pros and cons. If you play by yourself, for this example, I just choose C. When we play with others, we let them, of course, interact and choose. But now, in this sneak peek, I'll just show you. And here we have establish new industries, which is also one of the missions. But unfortunately, we don't have enough money but you can see it's transport by truck or by truck and ship, and this has a bit more climate adaptation in it. And here is this C has very much climate adaptation measures in it. But we have to choose to do nothing here. Now we have some money left in the wallet, and just because we can, I bump this one up by 2,000 before we take the next time jump. So this game, it enhances the players' understanding of the effects of the climate change and how to adapt society to it. But it also enhances the analytic abilities and the understanding of complex decision making, which we all know is part of the process. So this time we were a bit luckier with the weather. We had a 3-day heat, 2 3-day heat waves and 1 10-year drought. And as the result of that, we save lives, and we have 4 of the SDGs pointing upwards and 1 pointing downwards, and we have some money for the next time period. So now we have seen 4 out of 7 missions, and I'll see if we have time. I don't see the clock here when I show the screen, but I've clocked myself, so hopefully I will stay in in the time period. Anyhow, you see that we have 1 of the SDGs with the double arrow that we want in all 5 of them. So I'm doing so. Here we have the mission of saving drinking water, because climate change affects also the drinking water and supply of that by heavy rains, increasing chemicals and microbial contamination. And also we can have a lack of water during droughts. Well, let's see A. Here we have information, which could be a pamphlet or perhaps a website. And we have water tanks and we have a water protection area established around the water tower. So then we see that it affects 3 of the SDGs positively, and what the cost would be if we get hit by extreme weather. For B, it looks like this. We have the same measures as in A, but we also have moved the water treatment plant from the industrial area to a better place. And we also build a wetland, which increases this life on land SDG. And then, as I showed you before, you can see how it affects how we are affected by heavy rains. So I'll just choose B here and jump to the last one that I can show you, which is new housing in the woods. This is a bit trick question, almost, because you will cut down woods to be able to do a city, but we recognize the city or the A and B and C from the densifying the city. It's almost the same, with carpool parkings at option B and C. But I'll choose to not do any of this because it affects the SDGs the best, I think. And then we do a time jump. Now, I'm aware of that we have money left in the wallet, so I could have spent them in some of the missions that we had. But I think that we have run out of time. So if you think that this seems like a fun way to get a discussion started, then you're very welcome to use this tool. I think I have used my 15 minutes here.
Yes, I know. Thank you for a truly inspirational talk. The chat is piling up with questions, so I do think that you need to go and answer them during the break. But I must, because I'm an Uncle Scrooge, I'm thinking that it's my money and I want to keep it. So what if there would be that kind of an option that you wouldn't spend any money? What would happen then?
Oh, it depends on which weather we have. You can get quite a good result by not spending any money, just taking X on everything. But it really depends on if we get hit by heavy rains or a 100-year drought, then it wouldn't go too well for you.
That's what I think. So
Yeah.
it's a good motivation to spend money. But all in all, this
Yes,
sounds
it
very
is.
interesting. But then there's a very serious question: do you play alone or with or against others? And how long does one game take?
Now we almost played through this game, so it takes anything from like half an hour if it's the first time and you read everything thoroughly. But if we play with a group of pupils, it takes about an hour and a half or 2 hours, because we have discussions and we divide them into subgroups, and it's a bit of a democracy learning in the same time. So you have to also argue for your stand, and then you have when you divide them into subgroups, they could end up in a group with.
Okay. Now I must say that thank you very much for all the talkers. You were truly inspirational, and I must say that for everyone, it's never too late to learn new things. And that ends for this afternoon's first sessions. Thanks a lot for joining.